Welcome to 3 Steps to Sketch. Today we'll look at a basic secant graph, y equals negative secant of x over 3. So here's our template for unshifted or basic secant graphs. And here's our equation with the grid. And before we get started, do notice that our equation is in that general form for unshifted secant graphs, y equals a secant bx. So that's how we know which template to be using. All right. Let's dive into step 1. We're going to find our companion equation and its essential information. So our companion equation is simply going to be our equation, but instead of secant, we'll use the reciprocal function cosine. So everything else stays the same, but we have y equals negative cosine of x over 3. So essentially we're going to graph this equation, and then we'll change it into the secant function. We'll do that in step 3. So if you don't yet know how to graph cosine functions, I will post a link for that in the video description. You definitely want to check that out before you start graphing these secant equations. All right, so back to analyzing our companion equation. We see a is the coefficient in front of cosine, so a is negative 1. All right, so that tells us our amplitude if we take the absolute value. So that's from midline to maximum or minimum. The negative sign tells us that we have a reflection over the x-axis. And without going into too much detail about that yet, let's just put a big star on step 2 so that we recall we have that reflection. All right, next is b. Now, b is a little bit hidden in how we have this equation written. If you'd like to write it as y equals negative cosine 1/3 x, that may help to see that b is 1/3. So b tells us how many cycles happen between 0 and 2 pi, and it also helps us find the period. We do that taking 2 pi and dividing by b. So 2 pi divided by 1/3 is actually like 2 pi times 3. So our period here is going to be 6 pi. And now that we know the information about our base graph, let's choose how to label our axes. So the horizontal labels are the most important in my opinion, and we are going to choose this very intentionally. Take your period and divide by 4. So 6 pi divided by 4 is going to be 3 pi over 2 when we simplify. And we do this so that when we plot our companion pattern in the next step, each key point will align with each horizontal tick mark. Makes for a nice, neat graph. All right, our vertical label, 1 will usually work really well. So let's take a minute to go ahead and label our axes. We'll start with the horizontal, and we're counting by 3 pi over 2. So we have 3 pi over 2, then we have 6 pi over 2, which is 3 pi. We have 9 pi over 2, and then we'd have 12 pi over 2, which reduces to 6 pi. So we're just adding 3 pi over 2 every time. All right, so we stopped at 12 pi over 2, so now we have 15 pi over 2. 18 pi over 2 reduces to 9 pi. 21 pi over 2. And then 24 pi over 2, or 12 pi. So I'm going to pause and label the negative part of this axis. It will be the same values, just negative. So if you're following along, feel free to pause and do the same. All right, so here's the fully labeled horizontal axis. Let's quickly label our vertical axis, counting by 1s. And we have a nicely labeled grid setup. Now before we move on to step 2, let's take a pause to find the asymptotes equation for our secant graph. I'll post some videos later on that go into a little bit more detail about this. For right now, we're going to go ahead and use this really useful setup where we take our inputs of our secant function, so that's x over 3, and set them equal to our asymptotes of our parent secant graph. And we should know that those happen at pi over 2 plus pi k. Okay, take a look at y equals secant x if you need confirmation of that. And note that k is simply an integer, so we can use this representation to create an equation that generates each asymptote along our secant graph depending on what integer we substitute in for k. All right, so again, we took our inputs of our secant function, set them equal to pi over 2 plus pi k, and then simply solve for x. So to do that here, we would multiply the whole equation by 3, and let's write our final equation over in our template. So we'll have x equals 3 pi over 2 plus 3 pi k. So let's let k equal 0. We know that our final graph should have an asymptote then at 3 pi over 2. If you let k equal 1 and you do some simplification, you should see that another asymptote, the next one to the right in fact, will be at 9 pi over 2. Let k equal -1 to find another. So if k is -1, you should see that with some simplifying, you find an asymptote at x equals -3 pi over 2. So it takes a little bit of work to start to understand this asymptotes equation, but once you're familiar with it and comfortable with it, it's a really concise way to represent all the asymptotes of a graph. All right, now we're ready for step 2. We're going to plot our companion pattern. Make sure you do this lightly because this is not our final graph, so I'll use light blue here. And let's also notice the star here to remind us that we have that reflection over the x-axis. So our base cosine pattern with a reflection should be minimum x-intercept, maximum x-intercept. It's that reflection. Okay, so let's go ahead and plot these points. Again, plot lightly. Our first point should fall on the y-axis, and you get the y-coordinate simply by looking at the value of a. So our minimum for our companion equation, our cosine equation, happens at 0, -1. Then we have an x-intercept that happens at our first horizontal tick mark, moving to the right. And then our maximum will happen at the next horizontal tick mark, and the y-coordinate is simply the opposite value of a, so +1. We have another x-intercept at the third horizontal tick mark, right there. And then our pattern would repeat. So that would be the minimum of the next cycle. So here we have actually graphed a cosine equation. We graphed our companion equation. And now we're finally ready for the most fun step, where we recip, sketch, and repeat. So the cool thing with this method is we aren't actually having to go in and take literal reciprocals of all the y-coordinates. We know that the minimums of our companion equation become the local maximums or the relative maximums of our secant curves. And then our maximum from our companion equation, all the maximums become local minimums of our secant curves. So let's go ahead, we'll put on some basic points here to show the reciprocal, to show our secant graph points. This local this minimum for our companion equation becomes a local maximum. Our original x-intercepts become vertical asymptotes. Let's go ahead and put both of those on there from this cycle. And then this maximum turns into a relative or local minimum. Okay, so we have part of a secant curve here, another in this section, and then let's go ahead and put this portion of the local maximum here at 6 pi, -1. So this recip sketch may take you a little bit of getting used to, but once you're familiar with how the secant graph corresponds to the companion cosine equation, it becomes very easy. And the key is really knowing that changeover that occurs. So again, that's the minimums turn into local maximums and maximums turn into local minimums. And of course, x-intercepts become those vertical asymptotes. So now we can repeat for as many cycles as we need. So here we go. Let's finish out the curve here. We know that we can plug in different values of k in that asymptotes equation. Now's a great time to double check. Substitute in k equals 2, and once you simplify and combine like terms, you should get x equals 15 pi over 2 as another asymptote. All right, we have another curve here that has a local minimum. And if you're not familiar with that terminology, local minimum simply means within that small area, that local or relative area, that's the lowest y value. Okay, it's not the absolute minimum. It's not the lowest y of the whole graph, just in the small area. All right, let k equal 3, and you'll get the next asymptote here at 21 pi over 2. And you'll have a partial curve here for as much as we can fit on the graph. All right, let's work the pattern in the other direction. So there's that asymptote we talked about when k is -1. Another curve that has a local minimum. Another asymptote. I'm sure you can verify, but that's when k equals -2. Another curve that has a local maximum. another asymptote when k is -3. Curve with a local minimum. So you really start to feel the pattern here after you've worked a couple of these secant graphs. And we'll finish it out like this. This is 4 cycles of y equals negative secant x over 3. I'll post some more worked examples in the video description, and I'll also post some links to playlists on how to graph other trig functions, so check those out if you're interested. Thanks for watching.